Great.
All right. Well, I'll just quickly say thank you, everyone, for taking your time to join us. Professor Zhao Wei is speaking from Shenzhen at 11 p.m. This is the only time he can guarantee his availability, so we're deeply grateful for his time. This is the third lecture in the series where Professor Da Xuanfeng really started this along with several other distinguished scientists in discussing this topic. Is quantum knowledge still needed in the era of advancing quantum computing? Our previous conversations are all available on YouTube. I have been just here to provide logistic support in a lot of these things, and I'm just grateful to be part of it. Da Xuan, I'll give it to you. I'll let you to also introduce Professor Zhao Wei.
Sure. It would be a great honor to introduce my former boss, Zhao Wei. When I was at the Macau University, he was the rector, the European name for a president. Zhao Wei has a rather incredible career. He started as an undergraduate in physics in a school somewhere in China. I don't remember the school. Later on, he completed his PhD in computer science at the University of Massachusetts, and then continued to move up and up and up, and he became eventually the associate vice president for research at the Texas A&M University and the chairman of its computer science department. And later on, also went to NSF as a director, one of the directors. There's a technical name for it. I don't remember the name, but he's big shot in the computer science in the National Science Foundation. After that, he then became the dean of the School of Science and Engineering, I think, of school somewhere up in upstate New York. RPI, it's called. Rensselaer Polytechnic Institute. It's an interesting school because I think nobody knows how to spell Rensselaer, but it's pronounced Rensselaer, I know. And after that, he was recruited by Macau University to be the provost, to be the president. There he stayed over, 20 years?
10 years.
10 years. 10 years?
Only 10. Yeah, 10.
10 years.
Yeah.
And now he is in a school called in Shenzhen, which is the China's fastest growing technology center. Not just in China, looks like it's actually one of the major centers in the world. And they recruited him to build a university there. And I think that this is what he does. So when we have this series of lectures, I decided to ask him to give the speech, not because he's a computer scientist, but because of his interest in quantum computing itself, which I found out is not normally doing great research in the computer science departments in all these universities in the world. And more of the quantum computing is really done in the physics department, which is understandable. But today he's going to specifically talk about something that I think the computer science and the physicists will find it very intriguing, especially when the name von Neumann was introduced. So here we go. Wei Zhao, the screen is yours.
All right. Thank you, Professor Da Xuanfeng, and thank Max and all of you. Again, I'd like to especially thank for Da Xuanfeng because he was the one that triggered me to look into quantum computing when he was, I think, my international fair chief officer. He brought a lot of visitors. Some actually were in quantum computing. So although I was in administration, that triggered me the interest, and I've been learning the quantum computing since. as he told you, by training, I'm a computer scientist, although I do have my undergraduate degree in physics. So today, what I'd like to talk is the topic maybe will not please either computer science side or not the people in physics side. But I think that's something we're missing for both fields to understand each other and figure out what we should do and to really to to dig out the great potential of quantum computing. So we were going through. I try to go through slowly for the many basic parts like Turing machine, von Neumann machine, and then the quantum computer, and finally through my my introduction. Basically, I try to introduce you Turing machine, von Neumann machine from my eyes. That will figure out what to make a difference in quantum computer. How can we make a quantum computer better? That's the purpose. So first of all, let's talk about Turing machine. You heard this many, many times, but I need to be with me for 5 minutes with a purpose, okay? Turing machine start with, they have a tape, an infinite length tape. And on the tape, you can put information like binary bits, 0, 1, 0, 1, 1. That means this information can be discretely put on the tape. And there will be a head which can read the data, basically a specific bit on a specific position on the tape. Then there's a controller. A controller internally it has a state. Let's say currently is in the K. Then what a controller will do is it will say, it has, say, by rule transitions, such as, say, if we're in state K and if with the head currently reading a 0, then we'll replace 0 by 1 and move ahead to the right. And then switch state M. So think about it. So you are in state K and the head report say, I found the 0. Then controller say, okay, head, please erase 0 and make it a 1. And then say, move the head to the right. And then say, now we become state M. Then in the M, they can do similar things. Say, we are in the state M, we read the 1, maybe we keep 1, and maybe we move ahead to the left. So basically, the rules say you either keep it or replace it, or move to the right, to the left, and then say what's the next state, and so on. So in this rule, you can see that the 0 erased and replaced by 1, and the head now is in next position, and things can keep going. Normally in computer scientists, to describe how you transit from a state to another, you're using the state transition graph. You can see we're in state K. We now read the first read 0 is say we found the 0. If you found the 0, the next one say you replace by 1. The R say move right, and then you can see the arrow point to the M. So we're in the M state. M state you can do the similar things back and forth. This is the only thing I want to say about the Turing machine. Believe it or not, you can see this is very non-trivial, like a toy, what they can do. It can do everything current computer can do, right? You can say find the maximum number, you can do the multiplication, you can do division, addition, and you can find do the factor, integer factorization, all the computation you can imagine in an integer form, it can do it, okay? So I'm not going to tell you furthermore on this. However, the machine, as you know, it was invented by Alan Turing in 1936, literally only 90 years ago. Honestly, the machine was never really being used or hardly being used. Somebody did build it, as far as I know. but it serves really good foundation for computer science people to define what the boundary of computing. That means what kind of problem you can compute, what problem you cannot compute. Maybe if this is something new to you, let me just give you a very simple example. For example, consider now remember the tape actually the input. Okay, tape actually the input. By changing the tape, erasing back and forth, eventually when machine stops, then tape become output. Think about it, what's a program? A computer program actually is a sequence of bits, right? Computer program today will have many letters. The letter can be replaced by integer. So eventually a computer program is a big integer. So you can put on the tape. Now, if I put two computer program on the tape, you can do the two, right? Now, if I want to ask you, say, can you tell me if two programs have exact same behavior? All right, you can do the testing. You put the one program output is one, other output is one. You say good. You put a two, without doing the exhaustive testing. Can you say these two programs will have exactly same input output behavior? This problem actually is uncomputable. That means you cannot find another computer program which input be two program, output say yes, they are same, or no, they're not. So that's not computer. There are many interesting problems actually not computable. And for really real good applications, and honestly, nobody really use it. But nevertheless, that will trigger the people after him not too far. He invented in 1930s to invent something more practical. One of the big invention is by this great man called John von Neumann, right? What he did was he said, rather than we building that tedious tab or head moving back and forth, let's do something straightforward. He said, well, first of all, we will put the program. A program is a sequence of instructions. I'll show you a program in a second in the memory. You can see they do have a memory here, all right? And they also put the original data. For example, you want to addition, right? You have a program to the addition. You have a first adder, second adder put in the memory. So store that. Then the computer, which on the left part of this graph, would execute instruction one by one. So bear with me. It goes slowly. It was first of all, it's taking instruction from memory, right? It started by taking the instruction from particular location of memory. And after execute this instruction, it go to the next location. It go one by one. You have an initial location. You can say address 0. Then if the instruction stop, then machine will halt. That means we finish. Otherwise, the compute CPU will execute the instruction and go back to step 3, which is get the next instruction and execute. So it do execute the instruction one by one, one by one. So let me show you a program. For example, let's consider additional program. You want to add two numbers together. Let's say you put X, which is a binary number, in the memory cell 1001, and put the Y in the memory cell 1010, and you want the result be in 1011. So the program will look like this. It first says load X from memory cell 1001 into register R1. You can see on the left corner, we have a bunch of registers, which is a temporary location to put the older number there. So basically, you move a number from memory locations 1001 into R1. That's what the instruction will do. Next, we'll get the Y from memory cell 1010 into register R2, right? Normally, we have like a dozen registers. Then, next instruction is add R1 and R2, which actually value xy, storing that result in R3. So now R3 will have the result, but it's not in the memory. When you turn the machine off, the R3 number disappeared. So now you have to save R3 contents into memory cell 1011. So that's the program. Next instruction will be stop, then program finish. So as simple as this. Now, although this looks like tedious, at least I can describe to you how addition being done by Von Neumann machine. In Turing machine, actually, I'm not daring to show you that. It takes us a half hour to show you a Turing machine, which indeed I can add two numbers together. So that clearly tell you the difference between Turing machine and Von Neumann machine. I don't want to go on the whole list here. I can give you the PDF here. Well, what I want to say is the very first line. The intuitiveness to everyday user, Turing machine has been too tedious for everyday user to effectively program. Although theoretically, Turing machine can do all the computing, nobody dare to build a computer and use it. In the contrast, Von Neumann machine, although still a bit too tedious, but you can see at least when we do the addition, I can show you which aligns sufficiently with intuition like me, a three-man, I can make a program to show you. See, in 5 minutes, I can show a program to you. I truly understand. I believe you would understand. So that's the difference. That's the difference. However, fortunately, the whole world did not stop on Von Neumann machine. We moved on. So when we moved on, people build additional hardware and software tools to make Von Neumann machine even more usable. Number one, we invent I/O devices like keyboard, mouse, screen. So that makes things a heck of easier, right? Because before that, the Von Neumann machine had a memory. You didn't ask me how the things being put in memory. Literally, you had to use electronic switch to turn every memory cell into a number. That's very tedious. Now, if you use a keyboard and mouse, it's easy to input output. And also, when the result stay in the memory, and now we can use the screen to see what's inside the memory, right? Actually, now we are watching the screen. The screen you're watching is because your memory actually has all this data in the screen, and that they want to show you. Another beautiful thing is people think even using machine instruction, as I say, load memory cell 1010 from memory and into R1, people think that's still too low level. So people build high level languages. For example, you can say English like say, if X larger than Y, then we do something. Then when you write this high level language, then of course Von Neumann machine cannot understand. Von Neumann machine can only execute instructions. So people invent something called a compiler that translate high-level language, which is like English, daily English, into machine language, like load X, load Y, let R3 be R1 plus R2, and if R3 larger than 0, then what to do. So when you have these two tools, and actually in the early 80s, and Bill Gates, the personal computer with DOS, which only has one user and only can do one task, then the kids can play, right? So computer become street kids playable. Then at the same time, we invent something called operating systems. What the operating system did is it allowed one CPU, remember, only one CPU inside your cell phone can do multiple things, right? You can see the kids now is hearing some music and play video game, and actually phone also is working on try to receive a phone call from somewhere. So even cell phone, you can see it simultaneously can run many apps together, and that's because you have an operating system which literally schedule the CPU to let different tasks use computer in a way such that you feel many things you can do at the same time. So this is what we did beautifully. However, computer science people did not stop there. Given the success of Von Neumann machine and the usage, the series computing theory actually being established. Early on, the computer theory only focused on what the problem can be computed, what the problem cannot be computed. I'm pretty sure you're familiar with mathematical work. For example, in mathematicians, normally they talk about, say, if a limit will be converged or not. Okay? Hardly they will talk about how a limit, the process, will converge quickly or not. For them, converge or not converge is critical, right? And how quickly converge is less critical. However, how quickly converge is like how fast you're computing. So computing theory, first part was done with the Turing machine about computability, what the problem you can compute or not. However, once we use the computer for many other things, like Von Neumann machine, then people seriously, how can compute faster? Or do we have a problem we never can compute faster? That's a very scientific problem, right? Normally, if you're not in computer science, you never heard about this term. You think computing fast just build a faster machine. The issue is even you build a very, very fast machine, some problem you still cannot computing fast. So that theory is called time complexity that measures how efficiently a computer can solve a particular problem. For example, let's say we found a maximum number in a given n numbers. I give you n numbers, say 10, 11, 13, 1, 99, 200, 11, blah, 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 blah. I give you n numbers. I say, please find out which one the largest one. What do? Normally, you do n minus 1 comparisons, right? You compare the first two, see which one is larger. Let's say you tell me 3 and 2. I say, well, 3 is bigger. I remember 3 is bigger so far. Then I move to the third number, compares 3 with third number. If it's 100, I say 100 not bigger. So I do the compare n minus 1 time. When I finish compare that, I know which one is the maximum. Then clearly the computation time, what you did, you compare n minus 1 times. If n get bigger, you compare more. But the time is linear to n, so that's O(n). We call O(n) is the time complexity of the problem. Okay, as simple as that. And you will say, well, that's not too big a deal. However, computers, I think this is a contribution by computer scientists. They do find something very interesting. They actually classify the computing problem now into two classes. One is the easy class, another hard class. Easy class means time complexity is a polynomial function input size n. That means it's O(n) x, O(n) case k. That's it. However, if time complexity exponential function input size, then we call it hard. That means computation time will grow exponentially as input size n increases. You will be interested, you say, do you really have a problem which is hard class? Unfortunately, we do. For example, integer factorization, right? If I give you a number which is n digits, then to find all the factors of this number, which actually will take exponential time. That means the time will increase as time will increase exponentially as increases. This means if you think about it, if n is say 100, you want to factor a 100 bits number, then it's e to the 100. That's a huge number. Literally, you cannot solve this in many years. So that means the von Neumann machine cannot effectively solve those hard problems. We actually have many of those problems. So that actually triggers for people looking for other computing device which can do better than von Neumann machine. That's a quantum computer. All right. So that's so far the von Neumann machine. But I really like to, not beyond that. So that's the first part. Von Neumann machine enable us to develop computing theory, part one computing theory, which is measuring how we are computing speed. The next thing, normally people don't talk about, but as Dr. Feng Hsuan told me, I came out because I want to compare von Neumann machine with quantum computer. I came out other two complexity. One is the design complexity. That means how much effort take for a human to design computer problem, solve problem. For example, if I say, let write a program to find the maximum number, you say, oh, that's easy for n for k equals 1 to the n, compare the two pair on one by one, and once you're done, right? For example, if you want to do a factorization, it's not hard either. You can say, well, given number, divide by 2. If divisible, then it has factor 2. Then divide by 3. If divisible, then you have factor 3, and so on, until you divide up to the square n, then you stop. So even the time taken is a long time. Actually, the program can be written down in a very relatively simple way. So people generally believe, although no theory yet, nobody will bother to say, oh, this program too complex, I cannot do it, right? Literally, I would say all the college kids, after 3 or 4 year training, he will dare tell you any program you tell him, he will find some way to write down the program for you. That's called design complexity. Von Neumann machine actually is good for that. Once we have a high level language and a compiler. Third is the managed complexity. Computer is expensive, and you certainly want a computer to do more things. So how can you effectively manage n simultaneous tasks in a computer? For example, when n increases, would it take more time to manage or not? Fortunately, the operating system so far did very well. Most time it's 01. It takes a constant time to manage it n tasks. For example, if I want to do what to do next, I pick one of the tasks on the top of the queue. So that's 01. Sometimes we do have to figure out who should execute the next. However, it's no more than on. So again, managed complexity has been kept pretty low in the von Neumann machine. So let me summarize. The power of a Neumann machine is it's not only itself is relatively intuitive, much better intuitive than Turing machine. Also, the use of a Neumann machine in early days triggered people to invent something even better and make the Neumann machine whole system more powerful, like an I/O device, like high-level language and compilers. Then, based on von Neumann machine and those tools that triggered to develop, I would say, the complete computing theory, which measure time complexity, how long it takes to solve a problem, and unfortunately, hard class is difficult for von Neumann to solve. I would say that's a great discovery by computer scientists. And design complexity measures the effort taken for human to write a program. And so far we found, given the current programming language compilers, and the whole system can be very efficient. And the managed complexity, how can we manage n tasks in a computer? And current all operating system very efficient to do that. So you can think of von Neumann machine is not good to solving the hard problem, hard time complexity problem. Otherwise, von Neumann machine did pretty well. That actually triggers for people to invent a quantum computer. Actually, I'm pretty sure you guys know quantum computer probably better than me, but nevertheless, I want to go quickly because I want to make some points. So first we have quantum bits, and quantum bits means this particular qubit has two base states, and they can superposition together. Normally, we express them in a vector form, right? This is for you guys from a quantum physics. That's pretty straightforward, right? Then computing means you have to convert bits from one way to another. So first we have so-called single qubit gate. That means the input actually the qubit, which have two states, A and B, right? Then output be Q prime. The, the, then the vector form is A prime, B prime. For example, then what really happened is the output actually is a complex matrix multiplied to the input. This is very critical, okay? Honestly, for computer scientists, they never can understand this. But nevertheless, given you are from physics, I assume you can accept this very well. So let me give you an example. If the matrix equals 0, 1, 1, 0, let's see what happened. The output equals this matrix multiply vector AB. When you multiply the result, is the result is BA. So what that mean? If the input is A, then output become B. Input B, output become A. Basically, you convert to the vector in two dimensions. So this actually called NOT gates. This is like in binary bits, you turn 0 into 1, 1 into 0. Then another gates we normally use is called 2 qubit gates. So let me quickly, I will not go through again. 2 qubit gates is you actually have two input have 2 qubits, output also have 2 qubits. Then again, it's a big matrix. You can see the matrix here. Do I have a mouse here? No, I don't have a mouse. Sorry. Then you have these two, the matrix M11, M12, M13, that multiply the input Q1, Q2, and give a result of A1, A prime, etc. So again, even the 2 qubits, this means you multiply the input vector by a complex matrix. Keyword is complex matrix multiplication, which convert input qubits into output qubits. An example would be a typical one we will see it here, our sort of truth table here. This is called a C naught. Engineering-wise, the Q1 is the control bit. Q1 is the bit you really want to manipulate. When Q1 equal to 0, then the Q2 will have no change. That means Q2 prime equal to Q2. When Q1 equal to 1, then the Q1 will flips. That's it. So that's called a C naught. Interesting enough, is the C naught being proven to be sufficient. Using C naught, you can build up literally all the computation as you want to. So now that came out so-called quantum circuit. A quantum circuit, basically you have input, say the 4 qubits, and every vertical line here means operation. For example, Q1 goes through the first knot, means it's being converted, become a Q1 prime. Then Q1 prime and Q2 go through the next gate, then and so on. So you can see here we actually have 1, 2, 3, 4, 5, 6, 7. We have 7 Q gates, and they make a sequence. They will convert Q1, Q2, Q3, Q4 into Q1 prime, Q2 prime, Q3 prime, Q4 prime. So now the quantum circuit is a sequence of quantum gates. Remember, every quantum gate is operated by a complex matrix. So you can think the whole thing is you have a matrix multiply to the input vector and get the next one. Then you can another matrix multiply to the input vector, get the next one, and so on. Basically, you multiply initial input Q1, Q2, Q3, Q4 by 7 times, you get the output, right? So in summary, we can say that we have a quantum gate, single qubit, and a CNOT. They are, we didn't talk about this here, but they are computation complete. That means they can do any computation function. Then quantum circuit is a sequence of quantum gates applied to the input qubits. Now, what's a quantum program? At this moment, quantum program is quantum circuit. That means if you want to write a quantum program, you have to actually write a quantum circuit. That's the reality today. And so that means the quantum computing, which is execution of a quantum program, means executing a quantum circuit. That means we were performing a sequence of complex matrix multiplication. Keyword is, if you want to make a quantum program, you have to build a quantum circuits. And result is the quantum program will perform a sequence of complex matrix multiplication over input qubits to get a result. That's it, right? So that's the quantum basics. The question really is, can every user think about a program in terms of complex matrix multiplication? This turn out, maybe for you guys in physics is okay, but for computer scientists, for our students, etc., we just found that this is intellectually challenged, literally intellectually impossible. For example, let's say I want you to find a maximum number given n numbers. I cannot, given I'm a chair professor in computer science, I cannot think of a sequence complex matrices multiplied to the input numbers and eventually tell me which one the biggest one. My brain just didn't work that way. However, if you tell me, say, using instruction or high-level language, I can do that, right? I can say, given n numbers, I compare them one by one, get the results. But here that becomes very difficult. So nevertheless, let's talk about a quantum computer specifically. You can have a single bit quantum computer, which only have a single one gate, and you actually can have a two. And what a computer bit is, this computer, first of all, is store 2 qubits on each blue star. Then in addition, the computer, the red line in the middle means it can do a 2 qubit gate operation. That means if you want to do a CNOT, it will do it. Then eventually it will turn the result in the same location. Or it can do 2 single qubit operation. It can do that too. So depending on what you want to do. Basically, it will hear the control information and do that one by one for you. This is a current, actually not very current. 2 years ago, IBM actually had this model being pushed out. It's 64 qubits computer. And due to the physical limitation, you actually cannot connect qubits arbitrarily. It connects in such a very nice way. Different quantum computers today have different ways in two-dimensional way to connect, but didn't go too far. So let's take the simple one. So given this so-called noisy intermediate scale, that means if you make other connections, the noise will be too big and the quantum computer cannot function. This is literally, people can accept the noise level. And for example, if we have a quantum circuit, this is 2 CNOT, input is x0, x1, x2. Now you given computer, what do? Then you actually can say, we let Q0 be x0, basically just like our using our von Neumann machine, let Q0 store x0, let Q8 store X1, and let Q16 store X2. Then the first thing you do is you execute the first signal operation. That means Q0 and Q8 will perform a signal operation. Next, what you do is you let Q8 and Q16 perform a signal operation. That's done. Then this is it. So you can see, given a circuit, given a quantum program, you can map onto a quantum computer like this 64 qubits computer and get it done. That sounds like easy now. Actually, sometimes challenge. For example, if you have a quantum program look like this, you first perform signal operation on x0, x1, then you perform signal operation on x1, x2, then you perform signal operation on x0, x2. Then use this quantum computer on the right. You actually cannot do it because it asks 3 qubits being connected like a triangle. But we don't have a triangle connection. For example, you put a Q0, X0, S1, Q8, then put the X2, Q16. Then ask Q16 perform signal operation with the Q0. We don't have that connection, so we cannot do. So what we do is we can do a transform. That means we do a swap. In the middle, we swap S1, X2. By swap S1, X2, now the X2 become X1, then X0 and X1 can perform the signal operation, the third signal operation. Then we do swap again, then we get the result. So now you can see that for given a quantum program, the first thing you have to do is to do a transform. So make sure that be executable on a quantum computer that map to do it, right? So by doing this swap operation, we can do that. Now, of course, it will take 5 steps to finish. So consider another quantum program. Again, this program can be executed that way. So what about if we have one program already running this way, now have a new program coming? Then you actually don't want to wait, right? Remember, von Neumann machine can run n tests at the same time. Now the things become interesting. A new program coming, you can put the Q2, Q3, Q16, Q64. You can put it here, or you can put a 41, 42, etc. So this becomes interesting. That means how can you do n program at the same time? So nevertheless, let's summarize. The quantum problem execution have the following challenges. Number one, the program may not fit with the topology of a current quantum computer, need to do a transform. This actually could be time consuming. Number two, if a program is running now and you want to run another program, current quantum computer cannot do that. Von Neumann machine actually can do that. If you're running a program now, von Neumann machine can say, we store everything back to memory and running next program. And we run next program for a while and store everything in memory and run next one. Von Neumann can use interrupt to do this, and quantum computer we cannot do that. So in the resource allocation, we do a best fit, and which can be time consuming to find out where the best fit to. So now the question is, can the time complexity control it on the own or less? That's a challenge. So now you can see, given this little bit tedious introduction lecture on 3 machines, Turing machine, von Neumann machine, and quantum machine, now we can have following comparison. For von Neumann-based computers, von Neumann machines, and unfortunately, it cannot solve the computing problem which is in the so-called hard class. Fortunately, very fortunately, at least we now believe quantum computer can do it. This is due to a great professor in MIT, and his Professor Short. He literally showed the people how to use the quantum computer to do integer factorization in polynomial time. Remember, integer factorization in von Neumann machine will be exponential time. So that's he did in the 1990s. And that, I think, really worth for Turing Prize or Nobel Prize, whatever. I don't know why he hadn't got a prize. That wake people up. They say, oh, if you can do that, maybe quantum computer can do all the hard problems. That's how to trigger the whole world to have the race on building quantum computers. The trouble is, until now, quantum computer had not been very, very useful. Why? It is because for von Neumann machine, we have an English-like language and compilers. So literally, a high school kid can write program in Pascal, C++, and compiler translate. Machine will run. In quantum computer, unfortunately, you have to think to programming in complex matrix multiplication. As I said, we in computer science found that's too challenge. Nobody dare to do it. Nobody has been successful doing it. And we don't have a tool to do it. That's the trouble. So that makes so-called program design complexity comparison unfavored to quantum computer. Quantum computer now, the programming effort is just too high. And however, for von Neumann machine with a high-level language, C++, etc., it is really, really low. Then on the operating system part, that means to manage the quantum computer still is not in a favored status. For von Neumann machine, the operating system, no matter the Windows or Unix or Apple, it's great. And no matter what the commercial brand is, through interruption of virtualization, and we have very low memory complexity, right? When you buy a cell phone, you don't feel somebody is switching n tasks inside your phone, which actually is happening. And however, for quantum computer, we don't have interruption, we don't have virtualization. You had to use computer for one thing, and then offload for another. That's very tedious, and so we need to develop that. So in summary, von Neumann machine integrate the early series, computer-based series, and technology into unified standard form, and enable to develop program design tools, and really drove the computer from laboratory to practical applications. For quantum computer today, as I said, we need a universal system architecture which can capture the quantum characterization. However, we really have to bridge the gap between theoretical foundation and engineering implementation. That means we really need the tools to do this. Otherwise, it's been really challenging. So, gentlemen, I don't know if I said anything makes sense. What I'm trying to say is really it's this table. To make a quantum computer useful, you have to solve the problem in the colored red. That means you cannot force a human to think complex matrix multiplication unless, we probably from Mars or something. The human on the Earth found that's very difficult. I know you guys probably can do, but other people found it challenge. And also we need to develop some kind of system tools to make OS-like tools for quantum computer. Maybe Professor Feng and Max and Professor Liu, I stop here. Maybe we can discuss.
Excellent, excellent. since Thomas is our guest here, Thomas, I'll give you the first choice to ask questions.
Hi, thank you, Prof. Feng. Thanks very much for the very interesting and somewhat maybe a bit, how do I say it, brings me back to a bit more very low level kind of computing architectural question, right? It seems to me like conceptually we have some form of a quantum computer. I don't know if we really had a good architecture yet. That's number one. Meaning that have we been able to design a good quantum computer with a good architecture, which means that it must somehow satisfy some of your other requirements from the computing point of view, right? Meaning how can I compute? How can I write programs? How can I maybe structure the computing circuits and so on so that it works and make life easy for some group of people and make the thing work, right? So it seems like there's the architectural design issues which still need to be clarified. That's one. Then of course from the user point of view is user is at a much higher level and you certainly, like you say, you need the OS and other software tools to be able to access the quantum computers, but the user would typically look at the problem from look at the usage of the quantum computers from the viewpoint of usage, right? Application is not so much like the low level kind of things that we are looking at, right? So what's your view here, Prof. Zhao?
Actually, I think you stated correctly. At least it's my view. You're using a really good word. I assume you do have a good computer science background. Architecture. The von Neumann machines architecture start right here, right? That's very critical. You can say Turing machine is simple, but it's too simple to have the usability. And the von Neumann machine, which I want to bring, von Neumann machine, although, the control unit, ALU, register, when you put together, you say, oh, high school can do that. Oh, well, high school can do that today, but in 1940s, when people look at the Turing machine, no one else turned the Turing machine into this form, into a architecture style form. That makes the whole thing very useful. So you're right. So for quantum computer, people now have a quantum. Literally, what the people in quantum computing do is they're building the quantum gates, very very powerful quantum gates. It's a very very big size, right? So that's certainly is a lot of effort from the physics point of view to make the quantum gates smaller and smaller. That's one dimension. However, think about it. If without von Neumann machine, if we just turn the cube into transistor and the VLSI, still it won't work, right? So just make a device smaller, it won't work. It's necessary, but it won't work. It will work only you have a meaningful architecture, which the architecture enable you to build many things on top of that. Without this architecture, I would say high-level language is not a reality. Operating system is not reality. The beauty, this, Professor Daxuan Feng and I discussed many times. I would label von Neumann is the smartest person probably over the last 1,000 years. Although theoretically speaking, his invention little or nothing, you say high school can draw that. What's the deal? Oh, well, nobody else did it. He's the first one did it. That's why we have this conversation now, is the Professor Daxuan Feng and I, we talk about this, and we think this is very much a missing piece. In computer science, people say add Turing is greatest, everything else equivalent. So what? And in physics, certainly people worry about how to make a device faster rather than architecture. So I think you're right. The architecture keyword and von Neumann create or invent this great architecture, although looks trivial.
Mm-hmm. Yeah. I mean, there's some other parallel kind of work where people are talking about neuromorphic computing, which is somewhat similar, but also maybe slightly different implementation. Some people are using some other form of like memristors and some other form of devices to enable that architecture. Now, but even looking at what you have here, like the register, right? I cannot figure out how the register in a quantum computer would kind of look like at the moment, and how it can retain, its value over time sufficiently so that you can process your data enough, you can retain it long enough that you can process your data and also to deal with the noise that might be present in the system. So from the low level point of view, yeah, there's still it seems to me there's still some technical problem to be solved, though some people have put up some, kind of computers out there, but I think there's still a lot of low level problem to be solved.
I agree.
Yeah,
But
it's really noise,
well,
noise and error correction.
yeah, well, certainly we need a great scientist in physics to make a quantum gates per se smaller, more efficient, more reliable, etc., etc. That probably take a lot of time. Think about it. When I played radio, the transistor when I was 6 years old. Obviously, the semiconductor device today is much, much more reliable than when I played in 1960s. When I bought a transistor, okay, I can tell you, no matter what the book tell me, the transistor works differently from the book, period, right? For example, I can design circuit, want a certain capacitor this size, eventually whole thing won't work. It takes a lot of effort. That trained me pretty well. It takes a lot of effort to debug the circuit to make the transistor because transistor did not fit the spec, period. But today, you can see we can massively produce the CPUs with millions and millions of transistors and which work simultaneously without any bug. So I think people physics great. That's necessary. However, we're missing this architecture work as well.
Yeah, it's somewhat there, just like what NVIDIA is doing with all the GPU, right? It's a bit a brute force,
Yeah, that's a brute
computational.
force.
Yeah.
That's a far away from. Well, it's just a little bit. I would say even not incremental change. Okay, it's just engineering twist. Of course, they made a lot of money. We're happy for that. Uh, but the von Neumann machine is not a simple engineering twist from a Turing machine. We need to give von Neumann this credit. I would say, unfortunately, he had not received this kind of recognition.
Yeah, I think the physics of the quantum gates, devices, and so on will probably dictate some difference in even in this particular figure that you have here, how you transport your data between the different devices and storage unit, registers, memory. I think would be probably a bit different, right? Especially close to the qubit devices.
Right. Well, the professor was from UPenn. I think he's more or less material science.
That's right.
Actually, if you think about it, it was the material science people made the semiconductor material which enabled the revolution, right? So we
That's
get
right.
rid of tube. Of course, material science is a part of physics, I would say, to some degree. So we will see what happens. Hopefully, we
Hmm.
can see something in our lifetime.
Yeah. Well, you
Well,
know, Thomas, you have more questions?
yeah, good. Thank you very much.
Thank
Okay.
you. Thank you. Good question.
You said, Wei, you said it several times when we discussed, and today you emphasize it again. I remember you telling me that the famous guy in Zhongguo Keda asked you to help his students to do complex numbers multiplications. Now, I thought we do that all the time in physics. But what you're trying to tell us that that's almost impossible to do computationally. So what am I missing here? What is it that is almost not doable that the guy from Zhongguo Keda has to beg you to help his students to do something I thought is rather easy? But I must be missing something here.
Well, let me just repeat the story, okay? That story triggered the conversation I had with the Professor Da Feng. Professor Da Feng and I, we have a common friend who actually is a great scientist in quantum computing called Jianwei Pan.
Yeah, from
And
Zhongguo Keda.
he actually received tremendous funding and make a tremendous effort to building a quantum communication network and a quantum computer. So one day he actually called me up. He said, "Well, wait out. I'm now building up a quantum computer. Uh, let's not go on specific what a computer that is. It's not relevant." He said, "Now I have a bunch of PhD students in physics. And I told him to make a program because remember he got a lot of money, millions, millions. So obviously sponsor will ask him to say, oh, he probably report say, I now finally built a quantum computer and how fast that is, da. Obviously the sponsor says, great sir, now show us how to work. Okay, we have a problems want to solve. Let's show the real problem solving for me. So one day he called me up. He said, "Well, Wei Zhao, please help me. And my PhD student in physics, they're good in physics. They are unable to program. Why don't you help them to program for me?" That triggered me to look into the much more detail. Then I eventually came out to him say, if the program is so-called a sequencing of complex matrix multiplications, we computer scientists cannot do that either. It's just too challenging for us. It's not intuitive. Theoretically, any computing problem, if you can solve by Turing machine, there is a sequence of complex matrix, they multiply together, equivalently will perform that function. But where that matrix is, how can you think that matrix from your head and write down? I think even the genius from the very good university just have trouble to do that.
Why is that? I think it's hard. Is that because the Turing machine way of thinking is more logical to us, more intuitive, or what?
No, Turing machine logical. The Von Neumann machine is intuitive, right?
Right.
This like right. Turing machine. As I show you, for example, let's see this program.
I remember that example. It was very straightforward to follow, intuitive, like you said.
Right. Yeah. This is a number, right? You know, you ask kids, high school kids, I give you a number, say 10 number, and can be arbitrary, input one by one, separated by common. And then you tell me which one is the largest. The high school kids can do that. High school say, I'll input the first two number, compare, remember which one larger, then input the next one, compare with this one, which one larger, keep it. Then input next one until all the 10 number inputted and compared, whatever remains the bigger one, that's the biggest one output. So the kids can think that way and write down the program, and the language allow him to write down that way. Now, given this program, you ask any high school kids or any chair professor of computer science, say, think about a sequence of metrics, complex metrics, and when they multiply, and they will find out which one is the largest number among n. It's just not intuitive. Right? If you, I guess you will have a grandsons or sons. You know, when you have a high school kid, you give him a relatively mathematical question, and he can say, "All right, I can turn the program to do it." But when you say think about the sequence of metrics, and they multiply together, will give me the output that way. It's just not intuitive. Maybe I will say that somebody from Mars was thinking that way. The human, our head.
This is such an important point of your talk. Let me show my ignorance again. You mentioned just now, you take any two numbers and then you compare them, and one of them is larger, you throw away the other one. Then you
Right.
bring in the next one, and whichever is the biggest one, the smaller ones you throw away. So at the
Yes.
end, you have the largest number. The
Yes.
problem with complex number is, what do you mean by largest?
Well, it's not like, no, I give you n natural, I give you n integers. You need to build the matrix, which do that comparison and
I
find the
see.
next one and so on.
I
Also
see.
need to do the iteration.
Uh-huh. I see.
It's the
So
same task.
Same task. I give you n integers, say 10 integers, say positive integers. You found the maximum for me. The high school student, if you
Yeah.
don't
Do it.
give a computer, he you know, it take me a while, say, all right, I'll do this, I'll do this.
Yeah.
It's kind of like in your speak, maybe it's like an algorithm, right? So
Yes,
when you
that's
want to find the
algorithm.
maximum number, you
Right.
do some kind of sorting algorithm, and
No,
you
but
can.
I understand that. All I'm
Yeah.
saying is, what does the largest of a complex number mean? Because there are two numbers there, A plus
No,
IB.
no, that I'm not
No.
comparing n
Yeah.
complex number. The input will be an integer.
Yeah.
Okay.
It could
Quantum
be
computers,
like you say,
quantum
it's a very
computer
simple
say,
problem, right?
right, quantum computer says, if you want to solve a problem, you need to give me a sequence of complex
I got it.
metrics.
I understand what you're saying now. Thank you. I understand. Okay, Max, question.
Yeah, I would go back to some of the more fundamental question because I'm not in physics nor in computer science. But the one fundamental question is going back to
Then you're nothing.
the title of our series, thinking about, do computer scientists need to know about quantum to work in this quantum world? And my takeaway, and I will stand to be corrected, is if someone come here magically build all those tools, allow computer scientists to program in a high level language, then they don't need to learn about quantum. But it seems like those two have not been built. Is that right? And what expertise does it take for, who do you expect to come here and build the tools? Are we waiting for another von Neumann, or is it going to be physicists who are thinking in like this?
This is the question of a Turing Prize plus Nobel Prize. You know, I'm not diminishing the quantum computer. Look at the high von Neumann machine being proven cannot solve the hard class problem. That means human do have a computational problems von Neumann machine cannot solve. So that's means the quantum computer or something much, much more powerful is necessary. So necessity of quantum computer is true. The only trouble is the current form, as Professor Liu said, current form of quantum computer did not have a meaningful architecture. On top of that, you cannot build a tool. Consequently, you cannot efficiently use it. So far it's only one human. Literally, if you ask computer science, less than 6 people they write down the meaningful quantum program, solve the meaningful problem. Number one, of course, is Shor, and he's an MIT professor. This guy's a genius. He's interesting. You guys need to look at that. He he was working in Wall Street for a while, made a lot of money. Then he came back to teaching physics. Then he figured out this quantum program, which can do integer factorization. This program, this problem, computer science declared it's a hard class. We cannot solve it. And Shor made it. But so far, we need many. So Shor is like a tooling. He showed you can solve one. However, unless everybody else can clone his head, we cannot do others. Actually, himself did not develop another program. If you think about it, if you look, let me go slowly. If in computing theory, if computing history, and in the early time, we do have several very smart people. They all literally came out of computer program one by one. Okay, you had to believe it. When I was a PhD student in the early 80s, I found it interesting. In 1960s, to do a matrix multiplication, people write a journal paper about it. And you can get a tenure for that. You can write a computer program to do a matrix multiplication. All right. What today you think, what's the deal? Well, somebody actually write down a very good journal paper. I truly believe he made a tenure probably in Stanford somewhere. So in the early days, the program actually is not that straightforward, but many people made the effort and all the problem literally solved. I'm even sure Professor Shor himself, he only write one program so far in life. He didn't came out number two. That shows, as Professor Liu said, the architecture and the programming tools were insufficient. Necessary, yes. Tools are not sufficient. Tools are not there. Who can do that? As I think Max is asking this, I don't know. I do not, well, me in computer science, we don't train people we do learn complex theory a little bit, but we certainly do train people to think solving a problem in complex metrics. We don't.
I see. I have another question, but before I go, Professor Liu or Dashun, do you have more questions?
No, you go ahead. Yeah.
Okay. The question I have is on the implication. People do say, say quantum computing has a lot of application potential in the current form of AI computing. Can you help us to understand and appreciate what makes quantum computers so efficient for, the kind of AI computing as we know it?
Well, AI computing, if now let's go specific. For example, why the GPU so powerful? GPU different from the Intel CPU is it did two things. One is, first of all, it's good for matrix multiplication. That's getting close, right?
Yes.
Because in AI, when they do the iterations, it turns out to be the matrix multiplication, not a
Yes.
complex matrix. So it's general number matrix multiplication. They do a lot of that. So the GPU is good for that. Second, GPU will not have too much accuracy. The number getting smaller, therefore you can computing faster. That's it. That's what AI today. AI is another story. We can find time to talk about it. AI, what AI mean? Now, before we have a real AI, computing people, me as a computer professor, we always tell kids you have to make computing correct. Zero mistake. Okay, zero mistake. That's you believe computer. When you do the bank, you say, "Oh, calculate interest for me." If computer did wrong, this is a bad computer. You don't like it. However, for certain problems, actually, certain hard problems, hard class problems, if you allow mistake, you actually can compute it much faster. AI people, from that point of view, more or less say they are willing to compromise with a little mistake and in exchange to reduce the hard class problem to easy problem. That's what they did.
Can you provide a bit more explanation on why, if you sacrifice accuracy, you can gain so much efficiency? Where is that because narrowing down the last parts is hard or something else?
Well, think about play chess.
Yes.
Okay. For example, you can make n moves. You can pick up n pieces and make a move here, make a move. You can make n moves. If you just consider make n moves, it's too simple. Then the good player would say, when I make one of the n move, how my other part will make, he probably have n choices too. Okay. Then when he makes that move, how can I play again? So you look several steps ahead. You need exhaustively search. I make a move. For every move I make, other player will make a move. So that's already n squared. Then for the n squared situation, I will make another n move. That's n cubed. Then you, and so on, right? So when you do that search, you literally want to say, if you want to look 10 steps, naturally you're looking n to the 20 moves. Think about n to the 20, be too many moves you can think about it. All right. So what you do is you cut down certain moves you think will not be useful to consider. Then of course you can be wrong. That's how the computer plays the chess. They literally just cut down the move. Say from when I make a move, I only consider 3 moves. Other n minus 3 were bad one. I don't want to consider. Then I make a 3, other party make m, I only consider say 3, now only consider 9 move. So you can see it cut down dramatically the computation time. Therefore, then you commit something, then you make a mistake, then you lost. Then most time you're right, but your computation time is saved. That's generally what the AI people did.
Can we go back to your some of your early one of your early slides where you start talking about quantum computing? I don't remember which one. Further back. Almost in the beginning where you start to talk about quantum computing. Yeah, right, that one. The next one.
Yeah.
Yeah.
Yeah, you want to see
Yes,
this?
I want to ask something here. Remember our original reason for these lectures is, do we need to know about quantum mechanics in order to do quantum computing research? That's the whole purpose of this series of lectures. Well, I haven't finished my question. When you write something like A0 plus B1, that's only done if you learn quantum mechanics, because that 0 is written in terms of the Dirac-Bra notation, and the other side, it would be also the Bra notation. Is the linear combination of the two is what you need to know in quantum mechanics, and in normal computer you never write it this way. So that's the only quantum knowledge that you need. And that A1 plus B1 must be normalized to 1. That's quantum mechanics. Because A1 and B1 square is the probability in quantum mechanics language.
Yes.
And beyond that, everything is computer science. Complex maybe, but it's quantum computer science. So in other words, if you just define these things earlier without even using the word quantum, you can do everything. because this is just touching quantum at the very now. Of course, to do this, you need to have a qubit, which qubit comes from quantum entanglement and so on. I mean, there's a lot of stuff behind it. But the need for quantum, your original idea that you don't need to know quantum mechanics, I now understand what you're saying suddenly. You don't
Well,
need
I
to know
think you're
quantum
right.
mechanics. All you need to know is to learn how to do A10 plus B11. That's it. Am I wrong? Am I right, Thomas? What do you think?
I think it depends on where you are in the food chain, right? Like I discussed, if you are the one that's now designing the quantum computers and doing the very low level kind of work, then in some way you kind of need quantum physics knowledge, just like even in our present day semiconductors, right? Semiconductors are quantum device. You have quantum tunneling problems, you have quantum electron transport and so on, right? But once you can solve that at the higher level, at the user level, you don't need that. Yeah, I mean you're kind of quite right? You don't need that, right? But at the low level, in order to make it work, you will need the quantum.
All I'm saying is A10 plus B11 is not something you would do in any normal computing science.
Yeah.
But now that you're doing quote unquote quantum circuits, you have to do this because quantum mechanics means linear combination of states. That's the only time you bring in some rudimentary of quantum mechanics here. Now, of course, technologically, when you start doing this and you need to do entanglement and so on, that of course is very deep quantum mechanics. But that doesn't come in any obvious way. Well, what do you think that way?
I think you're correct. Actually, even in the Neumann machine, the low level, we never open them up because low level will be logical gates. As long as you say, I understand logical gates, I don't need to know transistors, right?
Yeah.
For computer scientists, what they have to learn is to agree the qubits be superpositioned. That's actually a very important concept. As long as they agree with that, superposition with the probability A1, B1, that's it. You don't go further than that. Now
Well, the
basically,
superposition is important, but if you take out the word quantum, you can discuss everything that you have done today.
And for them to understand these gates, as I said, they have to agree every quantum gate is a matrix multiplication over input
Absolutely.
status vector.
Beautiful.
Right.
Yeah.
Then you don't go further. You don't need it's a people scientists in physics figure out how to do this matrix multiplication literally in 01 time. Right. The beauty is let me talk from time complexity point of view. If you do a multiplication here in normal computer, it will take, think about it, n to the 3 times. Okay, I don't know if you know this. Basically, you multiply n to the cube times. However, in quantum computer, you do this in constant time, just one shot, the whole thing being done.
Yeah.
That's how the time being saved.
Yeah. Yeah, it's very interesting because the word quantum now is almost in everywhere. Even Donald Trump seems to throw out the word quantum every now and then I'm sure he doesn't know jack shit about what quantum is. But he never stopped from using it. That's his problem, of course.
Yeah, in China, somebody is selling the quantum socks on the street.
Yeah. I mean, this is almost like
Yes, on the Taobao, I can tell you, people advertising this quantum socks.
Well, 15 years ago, everything you sell has the word nano in it.
Yeah, about to say that.
You know,
Yeah.
everything, your nano, whatever you do, you put a nano in front. So now quantum is the key word. But now we see that the only thing that a young computer scientist need to learn, or everything you said today, is that A10 plus B11, and write it in the way that Dirac put out the way. You know, Dirac writes this zero is wave function. He writes it this way. And,
Right.
and that's the only time quantum terminology is used here. Ah, this is so beautiful here. This is beautiful.
Yes. Well, that's why actually I admire people from physics. No matter how complex things is, and eventually it showed to the people in a very simple, elegant way. I think honestly, I'm glad I was a physics major undergraduate. I'm proud for that because that's in other part of science. Some people
Did you
make
take
things very
quantum
ugly.
mechanics as an undergraduate?
Actually, I learned only not very much detail because that's in the Cultural Revolution. We
I
spend
see.
time to working the farms,
I see.
not on the quantum computer.
I see. Well, this is very interesting. Thomas, do you think NUS students, how would NUS students react to a lecture like this today?
Uh, it dep I suppose it depends on the level. Maybe the senior and the graduate level would find this very interesting because it's somewhat thought-provoking and at the same time bring them new perspective of something that is coming on mainstream, right?
Great.
Well, I would say this lecture may be the middle of nowhere, unfortunately, because for computer scientists, I'm telling them they already know. They say, "Well, you're telling me von Neumann machine worked very well," and for quantum computer, especially people making the quantum computer, like Professor Pan, he may or may not like hear this because he's focusing on how to make a quantum computer, the whole computer, whole device smaller and more efficient. And what I'm saying is we're missing one piece, as Professor Liu said, the architecture of quantum computer.
Mm.
And that architecture should enable the higher level tools. As I said, many of us, or I would say entire science community, never gave von Neumann this credit
Yeah,
until we met a quantum computer. We found, oh, here, because we don't have von Neumann, and then we don't have architecture.
yeah.
I think that's really I want to say. So I'm
Well,
calling for von Neumann, but this may or may not help any high school kids or college kids who are looking for jobs.
a few years ago, when I heard about quantum computing, the narrative these experts say is, well, you know, normal computer can calculate so fast, quantum computer can calculate billions and billion times faster. From your discussion today, it's not obvious that it can go that much faster.
Well,
Uh,
it is. The integer factorization using Shor's algorithm can do it. It will
okay,
take 100 years. It
okay.
takes 100 years to do an integer factorization. Let
But
me
we,
just add a little bit more. Why I'm keep mentioning this problem? Because integer factorization is critical for decoding.
okay,
When you
got it.
coded your email,
Uh-huh.
literally you're using assumption integer factorization cannot be solved very quickly,
Yeah, yeah,
right?
Mhm.
So if integer factorization is successful, literally all the coding theory had to be redeveloped. So that's critical. And the quantum computer, once you build for many qubits, say like I will say 100 or 200 qubits, it will the Shor's algorithm execute the whole world will blow out.
Well, I'll give you a real example problem. You know, my PhD thesis, thinking back, is so trivial that I think it's almost embarrassed to tell people that I got a PhD with that problem. What was that problem? At that time, the problem is in nuclear reaction. We have my thesis advisor and I encounter a 6-dimensional integral with a rather complex integrand, and you have to integrate it 6-dimensionally. Now, at that time, the fastest computer, this is, by the way, in 2072, okay? I got my PhD in 2072. I'm so sorry, 1970, or what year is this? 19,
Should be 19.
1972, okay? Now, the fastest computer at that time, I don't know whether we even remember this, it's called CDC 7600. That's even before Cray. And so what do we do? Well, if you do it normally, you have to do one integral, 1 dimension, and then the next integral, another dimension. That means you have millions. So it becomes extremely time consuming. And the only time we could do one calculation is to go to Los Alamos, use this big CDC 7600 that you have, which will take 3 hours just to do one calculation. And that's just not possible. So my thesis advisor and I finally decided that to do it this blunt way just cannot work. I will never finish my PhD because I'll never do more than one calculation. So we eventually decided to look at it with using Monte Carlo method, Monte Carlo sampling of the integrand. So in other words, do some cheating, so to speak, rather than doing every integrand in its completeness. And it turns out that our calculation comes out to be as accurate as within 5 to 10%, which apparently is good enough for the experimentalists to compare our calculations with. Fortunately, I could get my PhD this way. Nowadays, you use the computer, the computers, whatever they have now. It will take literally minutes to do what I compute. So will quantum computer make this faster? This is a very practical question, Wei.
I will say yes. Because first of all, theoretically speaking, anything Turing machine can do, quantum computer can do it, and only can do better. And especially, you can go further for quantum computer, for quantum device, or generally speaking, for physical device. You can use the physical property to simulate computing in such a way you can do much better. Actually, integration, remember, integration is simulatable by physical properties.
Right, right.
And that simulation actually is the computing.
Right.
You call it quantum or not, doesn't matter.
Right, right. Very good. Well,
remember 那个叫古代那个曹称冲象，就是 simulating an integration problem by physics. Right?
Yep.
Okay.
Well, Thomas, any other last-minute thoughts?
Good, thank you. No more.
And Max?
No, this is great.
Oh,
Thank
by the
you so
way,
much.
you gotta write it up. This is so good. This is so good. Okay. Also, our
Wait.
discussion. Sorry?
You were saying you don't know who the audience is. I'll tell you at least one audience. I think the whole world is being crazy about quantum now, but I think most people do not understand quantum, neither from the physics perspective nor the computer science perspective.
Well, for people looking at A10 plus B11, they'll get blown away. They have no idea what that is.
You are just explaining it in a simple way, but no simpler way. I think this is as accessible, but also
You know, I
direct.
learned this direct notation when I was taking quantum mechanics at the graduate school. Undergraduate, even we don't write it this way. At the undergraduate days, we start to learn about the direct notations, which is the Bras and Ket
Right.
of Dirac.
Yeah.
Um,
Bra and Ket is Feynman's invention, right?
right.
I don't remember who invented it, but it
Yeah.
is so nice, you know.
Yeah.
And then if you do the complex conjugation, you just put it the other way around,
Yeah.
you know. And then you A1 plus B1 must equal to 1. And then A1 plus B1, A1 squared is the probability and B1 squared is the probability of that state. That's the end of quantum mechanics. That's all you need to know in quantum mechanics here. And that's why I say it is so beautiful for what Wei have said today.
Yeah, the way you made it accessible and in depth is truly special. So I think there is an audience. There's a wide audience for this.
You know, you may want to make this 2 slides, just a little, give a little historical context to where Bras and Kets come from. That would be that, and then you can say that's quantum mechanics. That's the use of the word quantum in this whole discussion.
Yeah,
That's right.
Yeah. All right.
Beautiful.
It's beautiful, and it's late for them, so we should let them go to bed.
Okay.
All right. Thank you.
Okay.
Right.
Goodbye.
Thank you, Max. Thank you, Dashan, and thank you, Professor Liu. And it's a
Yeah.
good dialogue. And let's continue this conversation. Hopefully, someday we have a really useful quantum computer. That's actually the purpose, right?
Well, that's right. That's
Yeah.
right.
Wait,
right.
is it okay if we put this on YouTube? I feel like this would be such a
Yes.
fantastic.
No
Thank you.
problem.
No problem.
Thank you.
Yeah.
Yeah, sure. Okay.
So remember, write this up, okay? Wei.
I'll try. Maybe
Okay.
we should write
Great.
together.
It's great.
Okay.
Yeah.
Okay.
All right. Bye-bye.
Bye-bye.